And we will start today the hypothesis testing. Okay? The hypothesis testing, it's a little bit similar to the confidence interval, but of course we can use the confidence interval to make some inference. It's not just estimation. For example, suppose that someone comes to you and they tell you that the, the population proportion is 0.419. Do you think that his claim is true or false? So according to this confidence interval, this one of course for 90%, 95%. This is 95% confidence interval for the proportion P. So what do you think? His claim is true or false? False. Why it's false? Because 0.419 is not within this range. It's out this range. So we can say no, his claim is what is false according to 95% confidence interval. You have to say that. Because if you change the confidence level, of course, you may have 0.419 within this range. So you have to say that this claim is false according to the 95% confidence interval. Okay? So what is the hypothesis testing? As you can see here, we will talk about the main goal of many research studies is what? Is to check whether the data support a certain statement, sometimes we call it a certain hypothesis, okay, or prediction. So when you do a research, you want to prove something, right? We need the data support our proof, our hypothesis, or to prove our hypothesis. So this is the main goal of any research, okay? These statements or prediction, we call it, as I said to you, hypothesis. About what? About the population. Because as I said to you, always our target is the population, not the sample. We just use the sample because we cannot find or we cannot measure all the subject in the population. So we take a random sample from the population so we can study the population from there. Okay? They are usually expressed in terms of population parameters for the variable measured in the study. So in statistics here, a hypothesis is a statement about a population. Statement about, of course, this statement is what is mathematical statement, which means maybe equal something or a specific value, greater than a specific value, less than a specific value. These are mathematical statements, okay? Usually claiming that the population parameter takes a particular numerical range of values, and of course we will see these hypotheses after our. So these are the steps of the hypothesis testing, or sometimes we call it the significance test, okay? As you can see here, first, the assumptions. You have to make sure that the assumptions are met. Second, what are the hypotheses? And you will know now, or after a while, that we have two hypotheses. Something we call the null hypothesis. The other one, we call it the alternative hypothesis. The test statistic. The test statistic, this is our lab. Our lab here. This will, or with this test statistic, we will calculate from the sample a value. Okay? And we will, of course, this value represents something in our data. Okay? So in step 3 will tell us if the data will support one of our hypotheses or not. Because of that, I said number 3 is our lab. Okay? And then we will calculate something we call the p-value or probability value. P for probability value. This probability value for the test statistic we calculated in the previous step number 3. Okay? And according to this probability, we will make a decision about the hypothesis, okay? And then we will write our final conclusion about the population parameter in this case. Okay. So for any test, you have to make sure that the sample size is large, especially if you are dealing with the average population or the proportion population. Why? Because until now, in this class, we assume that the average the average sample or the proportion sample are normally distributed according to the central limit theorem. So you have to have large sample size. So you have to check that first. Okay. The second assumption, as I said to you, is the shape of the population distribution, and as I said to you, it should be normally distributed according to the central limit theorem. Okay. The second step, as I said to you, the hypotheses. We have two hypotheses. The first one, the null hypothesis, and the second one, the alternative hypothesis. The null hypothesis, it's a statement about our parameter, and it will take a specific value. For example, the average is equal to 80. The average is equal to 75. The average is equal to 4. Okay? So it's equal to a specific number. But the alternative hypothesis, also it's a hypothesis about the same parameter, but has range of values. As I said to you, the alternative hypothesis means the average is greater than 68, for example. So any value greater than 68, here you have a range of values. Or the average is less than 4. So any value less than 4, this will be alternative hypothesis, okay, about the parameter. We have samples for the null and the alternative hypotheses. The sample for the null hypothesis, we call it H naught, as you can see here. And for the alternative, we call it HA for alternative. Okay? Okay. The test statistic, as I said to you, this is our lab. This will measure, or will this statistic will measure how far the point estimate falls from the population parameter we assume in the null hypothesis. Okay, so if you remember, this definition is close to what definition of Z score definition or T score definition. Same thing. By these two scores, we measure how far the estimate point from what? From the parameter. Okay? But here, the value of this parameter, we will find it from the null hypothesis. Okay? Or we will assume this value. Okay? So usually this distance is measured by what? The number of standard errors. So this, of course, emphasize that this is Z score or T score, as I said to you. After that, we will calculate the probability value for a test statistic. Okay? So, what is the p-value we'll do here? Actually, we always assume that the null hypothesis is true until p-value tell us something different. So again, we always assume that the null hypothesis is true, and this of course means the alternative is not, until the p-value will let us know if or give us evidence against H naught. How we will know that? Actually, if the p-value is too small, which means the probability is so tiny, okay, that means the p-value support the alternative hypothesis, not the null hypothesis. Or we can say that the p-value in this case has a contradiction against the a null hypothesis. But if it's large, the p-value, this probability value is large, of course, this supports the null hypothesis. Okay? As you can see here, the smaller p-value, the stronger evidence against what? H naught. Okay? So the p-value, as you can see here, we summarize how far out in the tail the test statistic falls by tail probability of that value, and the values even more extreme. What that means, and I know that it's difficult to understand, but actually it's so simple. Suppose you have a normal distribution like this, okay? For the mean, for the proportion, doesn't matter, okay? So where we can find the p-values, or we calculate p-values under this curve, how? Because it's a probability value. We calculate them from the normal distribution or t-distribution. Both are symmetrical distribution. You will find them at the tails. Don't forget that here in the middle, you have the mean, or the population parameter, mu, okay? I will say here mu naught, because this value will be related to H naught. Will be related H naught in the middle. So what do you think? Suppose you calculate the probability and you found the probability here for the test statistic. We have here the test statistic value. What do you think? If you find the probability is here, so what that means? Is it normal, or we can say it's a usual value or unusual value? If you find the probability in this area, of course will be extreme, unusual value. So of course this doesn't support H naught. So the p-value now, if the p-value this area, so what that means, it's so extreme, so it's so far from the middle, so that means it doesn't support what? The null hypothesis. But if the area is so close, so for example, it's here, for example, like this, and the test statistic is here, this value here, test statistic. So as you can see, it's so close to the middle. So this is support for what? For H naught, for the null hypothesis, not for the alternative hypothesis in this. So you will find always we calculate the p-value for the test statistic at the tails to see it's far away from the middle or they are close to the middle. Okay? And as I said to you, the smaller the p-value, like here, the stronger the evidence against H naught. Okay? Actually, we have the same chart here. Okay? This is what I talked about. So as you can see, this is the definition of the p-value. The definition. It's a p-value is a probability that the test statistic equals the observed value or even more extreme. Okay? So because of that, we find these areas at the tails of the distribution, because more extreme at this value or more extreme values. Okay? So as I said to you, we always assume that the null hypothesis is true. We always assume that until the p-value give us a probability close to the or large probabilities. That means this evidence provide or the data provide evidence with H naught, or a small p-value which give us strong evidence against H naught. Okay? Okay, so what is the cut-off point in this case? For example, the p-value should be equal to what? So I can say it's too small or too large. Okay, so we need here what? A cut-off point. So we can, based on it, we can determine if the p-value is too small, so we have strong evidence against H naught, or we have large probability. So in this case, we don't have a strong evidence against H naught. Okay, so in this case, we need something called the significance level. Significance level. As you can see here, the significance level is what? Is the cut-off point. Usually, we give the significance level this simple, alpha. This is, of course, a Greek letter, okay? Alpha, okay? So, alpha is the cut-off point that we will compare p-value with it. And we will say, if it's greater than, of course, we have here, as you can see here, we have a rule. As you can see, if the p-value less than or equal to 0.05, so we reject H naught. Reject H naught means we don't have strong evidence against H naught, against the null hypothesis. But if the p-value greater than 0.05, so in this case, we don't have enough evidence to reject H naught in this case. So these are the two decisions we will use about the hypotheses. As you can see here, we make the decision about what? About H naught, not HA. Why? Because H naught has just one value, but HA maybe have more than one value because we have range of values. We will not be able to find the probability for all the values greater than 0.4, for example, or less than 0.6, for example. We have a lot of numbers, so we will not be able to find the p-values for all these numbers. So we can find the p-value for just one number. And this number, we can find it at H naught, because H naught takes just one value. Okay? So according to that, we make decision about H naught. So if you reject H naught, you accept the alternative. If you fail to reject H naught, so you reject what? The alternative. Okay? Because we just have two hypotheses. Okay? So as you can see, this is just a chart about the p-value and the significance level and the rule of decision. As you can see here, we reject H naught if the p-value less than or equal to 0.05. Okay? And we don't reject H naught, of course, if it's a p-value greater than 0.05. Okay? Of course, we can change the significance level. Instead of 0.05, we can make it, for example, 0.01 or 0.1. We can change also the significance level. And in this case, you will compare again between the p-value and the confidence level. If it's less than or equal, so you reject H naught. If it's greater than, so you don't reject H naught, as you can see. Same idea. So the conclusion, this is the final steps for our hypothesis testing. The conclusion, based on the comparison between p-value and the significance level. Okay, so you will say, we have support evidence to H naught or not, in this case, if you will reject the null hypothesis. We will see that in our first application about the proportions. Okay, so we will apply these 5 steps on the proportion, and we will start with this example. I will go with the steps without any calculations first, and then we will do the calculations so we can finish the test at the end. So as you can see here, we have astrologer prepares horoscopes for 116 adult volunteers. Each subject also filled out a California Personality Index, a CPI survey. For a given adult, his or her horoscope is shown to the astrologer along with their CPI survey as well as the CPI surveys for two other randomly selected apps. That means we will have here three surveys. Of course, one of them is the correct one. Okay, so the astrologer is asked which survey is the correct one for that adult. So what is the proportion or for the correct survey here? It will be 1/3, right? We have three surveys. One of them is the correct, so the probability of success is what? 1/3, right? So in this case, we randomly, we can guess that the P, the population proportion, is equal 1/3, right? But maybe the astrologers claims what? No, it's not equal to 1/3. It's greater than 1/3. This is the claim of the astrologer, and we want to test or to check if this claim is true or false. Of course, you can do that not by this claim, but with this claim. Why? Because here you have just 1 point, one number. You can find the probability for it. But you will not be able to find probability for all values greater than 1/3. So it's hard. So in this case, you can formulate your hypothesis by this way. The null hypothesis, the population proportion is equal to 1/3. But the alternative hypothesis, it's the claim of the astrologer, so it's what? Greater than 1/3. P greater than 1/3. So this is the null hypothesis and the alternative hypothesis. If you remember, the first step is to make the assumptions. What here we are talking about what? The population proportion. So don't forget that to have the sampling distribution of the sample proportion is normally distributed, you have to check two things. First, n times b greater than or equal to 15, and n times 1 minus b also greater than or equal to 15. Once you have this, that means the distribution of p hat is normally distributed. So this is one of our checks. Of course, when we are interested in the proportion, that means our variable is categorical. It's not numerical. If it's numerical, that means we are interested in the average. Okay? But if it's categorical, that means we are dealing with the proportion. We are interested in the proportion, not the average. Okay? And of course, the more important thing is what? The data are obtained using randomization, which means you have a random sample. A random sample. And of course, if the sample is large enough, so you can have a normal distribution or to apply the central limit theorem in this case. So you have to check these steps. And then, as I said to you, I will talk about the steps first and then the calculations. Something about the hypotheses. As I said to you, always, the null hypothesis is equal to specific number. Always. So because of that, we have what? Equal. Always H naught, the null hypothesis has equal. P, the population proportion, is equal to a specific number or a particular number. This number we call it B naught. Okay? Always. But the alternative hypothesis has different forms. For example, maybe someone comes to you and they claim that no, the population proportion is not equal to this number. It's greater than this number. So you have this alternative hypothesis. Okay? We call, of course, based on the direction of the alternative hypothesis, you will know the type of the test. Here we have actually three types. Some people say two, some people three. I prefer to say three, not two. When you have greater than, that means you have one-sided test. Okay? But I prefer to say it's right-tailed test. Right-tailed test. Why? Because when we calculate p-value, we will use the right tail. I showed you here. You will use the right tail. This will be obvious in this case. If the alternative is less than, as you can see here, the statement here has less than. Also, this is one-sided test because you will use just one tail to find the p-value. But this tail is what is left-tailed test. So it's the left tail, not the right tail. So because of that, you have this shape. The third test is what? Is two-sided test. Or sometimes we can say it's just two-tailed test. Here you have two-tailed. You will use both tails to calculate the p-value. And you will find the null, the alternative hypothesis has not equal. Not equal, of course, maybe what? Maybe greater than or less than. So because of that, we have here two-sided, the two tails. We will use them to decide if it's a true or false claim. Okay? So these are our three types of hypothesis testing. Right-tailed test if the statement contains greater than. Left-tailed test if the null hypothesis statement has less than. Two-tailed test or two-sided test if you have not equal with the the alternative statement, as you can see there. Okay. The test statistic. As I said to you, the test statistic is varies from test to another test based on the population parameter we are interested in. Because we are interested here in population proportion, so our test statistic is Z, okay? And the Z here is what? Is P hat, if you remember, P hat is what? X divided by N. X is number of successes and the sample size. Minus the hypothesis value of P, and of course this is what we can find it from H naught. If you remember, H naught is P is equal to B naught, so this value will be here, divided by the standard error, and the standard error is what? B naught times 1 minus B naught divided by N. Okay? So if you remember the confidence interval for the population proportion, it contains what? The point estimate P hat. We already have P hat. The standard error, right? And this is the standard error. And what? Z, right? But Z here, we calculate it. There, we find it from the distribution. Here, we calculate it, and then we will find the probability for it. Okay? So there's some similarities between the confidence interval and the hypothesis test. The p-value. As I said to you, based on the direction of the test, you will calculate the p-value. Okay? So, if the test is right-tailed, and the right-tailed means what? The alternative hypothesis has greater than. So in this case, the p-value, you can find it by this way. The probability that Z greater than the test statistic value. So Z not here is test statistic value. This one. This is the value of Z. We will use it here, okay, to find the p-value. So it's greater than, which means you need to find this area, okay, of course from the table or by itself. This is if you have right-tailed test. If you have left-tailed test, so you will use what? the probability that Z less than negative the value of test statistic Z. Because in most cases, because it's less than, you will find this test statistic Z is negative. It's not positive. So you will find what? Z naught, you will find it here, and you need to find the p-value, this area to the left of Z naught. Okay? If you have two-tailed test, so in this case, you need to find what? This area and this area. Okay? And do you know that this area is equal to this area? So just once you find one of them, you can just multiply it by 2, so you have both, right? So if the test statistic value is negative, so you will use this one. If it's a positive, so you will use this one. Okay? So these are the different calculations for p-value based on the direction of the test. Okay? And at the end, you make the conclusion. You will compare between the p-value and the significance level alpha. If it's less than or equal to 0.05, for example, so you reject the null hypothesis. If it's greater than, the p-value greater than the 0.05, so you fail to reject the null hypothesis. Okay? Let's do the calculations now. So this was the story how we will apply these steps on this question. Okay? But let's do the calculations. So first, the assumptions. From the scenario, you know that the variable is categorical. Okay? So you have correct or incorrect. This is the first thing. The second thing is the sample size is large enough, so we can assume that the distribution is normally distributed for the sampling, for the sample proportion. We have to check that. Okay? So if you return to our scenario here, we have what? 116. This is N. Okay? 116. And we will multiply it by P. And 1 minus P. If the results are greater than 15, so we can apply the central limit theorem and we can continue to perform that test. Okay? So as you can see here, N 116 times 1/3, so it's 38.7, greater than 15. What about N times 1 minus P? So it's 77.3, greater than 15. So we can apply the central limit theorem, okay, and we can continue, or all assumptions are met for this test, okay. The hypothesis, as I said to you, P is equal to 1/3. This is the null hypothesis. The alternative, P is greater than 1/3. Because it's greater than, so what is the type of the test? It's right-tailed test. This is very important to know from the very beginning, because you will know which tail you will use to find the p-value. So it's very important to know that. Okay? So it's right-tailed test. Now calculate the test statistic. We need to know the value of this test statistic. So find the standard error. 1/3 times 1 minus 1/3, so it's 2/3 divided by the sample. The sample size. So you have the standard error here. Okay. From the experiment, we found that out of 116 adults, they predict 40 of them predict correctly. So P hat is X divided by N. So it's 40 divided by 116. So it's 0.345. So this is p hat. Now you can find the test statistic value. So it's p hat minus p naught divided by the standard error. B hat 0.345 minus 1/3. This is B naught, or the hypothesized value from the null hypothesis, divided by the standard error. So you have 0.26. Now, next step is to find the B value for 0.26. Look at 0.26, it's positive. Why it's positive? Because it's what? Huh? Right-tailed test, greater than, okay? So to find the B value, you will apply our probability, the probability that Z greater than 0.26, okay? If you would like to use the table, so you will apply what we learned from chapter number 7, okay? When we talk about the normal distribution, how we can find the probability from the normal distribution, because the table always gives us the area to the left. So if you need to find the area to the right, like here, will be 1 minus the area to the left of Z. Okay? Because we can know this area from the table, but we cannot know this area. So it's 1 minus. Okay? So will be 1 minus the probability that Z less than 0.26. Go to the table. Find, after you divide this number into 0.2 and 0.06, okay, you will find the intersection between the column and the row. So you will find the probability is 0.6023. Say 0.6. Okay? So now the B value is what? Is 1 minus 0.6, so it's a 0.4. So this is the B value. As you can see, the B value is here. Okay? This if you would like to use the table. But if you will use the Excel, and I also prefer that, to use the Excel, to use the technology, okay, because it gives you the result will be more accurate than the table, okay? So you can use the Excel function, 1 minus norm.s.distribution, put here the test statistic value and the true, because it's a cumulative what? Cumulative probability. You will find that the answer is 0.4 something, of course, but you can round it to 0.4. So the B value is 0.4 now. We need to make a decision. So you have to compare between 0.4, the B value, and what? The significance level 0.05. Is it greater than or less than? Okay. So this is greater. Okay. So the 0.4 is greater than the significance level 0.05. So what is the decision now? Let me return to that table. Do you remember that table for the You reject the null hypothesis if the B value less than 0.05. But in our example, B value is 0.4. It's greater than 0.05. So we'll do what? We will not reject what? The null hypothesis. We don't have enough evidence to reject the null hypothesis. Okay? Yes, always, always, always. If you don't have different significance level, you assume 8.05. Okay? But if you have significance level in the question, say for example 0.01, so you will compare it with 0.01, not 0.05. Okay? So as you can see here, 0.4 is greater than the significance level, so the decision is failed to reject the null hypothesis. So what that means, the sample we have doesn't give us strong evidence against what? The null hypothesis. So what that means, the claim of the astrologers is what? Is false. So we would not conclude that the astrologers have special predictive powers in this case. Okay? Okay. another test, this time for two-tailed test or two-sided test. If you remember, if we have the alternative contains not equal, this statement contains not equal, so what that means, you have two-tailed test. What that means? That means when you calculate the p-value, you will use both tails. Okay, very important with that. So as you can see here, the p-value is two-tail probability under standard normal curve. Again, when we calculate the probability, you can find one of them and then double it or multiply it by 2, as I showed you in the previous slide. Look at this example. We have dogs detecting the cancer by smell. Study. Investigate whether dogs can be trained to distinguish a patient with bladder cancer by smelling the compounds released in the patient's urine. The experiment here, each of 6 dogs was tested with 9 trials. In each trial, one urine sample from a bladder cancer patient was randomly placed among 6 control urine samples. So the total is what? Is 7, right? And one of them is the correct one, the correct sample. So the proportion we are talking about here is what? Is 1/7. 1/7, okay? Okay. The results, in a total of 54 trials with the 6 dogs, the dogs made the correct selection 22 times with a probability of success 0.407. So this is what P had. So here we have P. P or P naught is 1/7. But here from the sample, P hat is what? 0.407, which is 22 divided by 54. So this is P hat. The question now, does this study provide strong evidence that the dog's predictions were better or worse than with random guessing? Look at the question here. It said what? Better or worse? Better or worse? So, greater than or less than. So both together is what? Is not equal, right? That both direction, as you can see. So first we have to check what? The assumptions. Okay, so we need to multiply n times p and we see if it's greater than 15 or not, and the same thing for n times 1 minus p. So we will know if we have a large sample. So 54 times 1/4, it's 7.7. Oh, it's less than 15. And if you multiply it by 1 minus p, 6 divided by 7, so it's 46.3. So this one is less than 15. So it's not large enough sample. It's not large enough sample. Okay? But we will continue with this example. Okay? It's just to know that when we have two-sided test, it's always robust test. Even the assumptions here is not satisfied. So the hypothesis, as I said to you, always the null hypothesis has equal sign. So the population proportion is equal to 1/7. Because the question said better or worse, so here you have two directions, so the alternative will be not equal. Suppose we change the question here. Does this study provide strong evidence that the dog's prediction were better than with random guessing? If it's better alone, this means you have here right-tailed test. If it's worse alone, so it will be left-tailed test. But here, because we are better or worse, so it's a two-tailed test. Okay? So in this case, the alternative is not equal to 1/7. Okay? The test statistic, we already know it. to remind you, so it's b hat minus b naught divided by b naught, 1 minus b naught divided by n. So b hat, we already have it, we calculate it. B naught is 1 over 7, and 1 minus b naught is 6 over 7. N is equal to 54 from the question. So we have z equal to 5.6. Okay, 5.6, we need to find the b value for this value. Okay, but here we have what? Two-tailed test, and the value is positive. So in this case, we can use 2 times the probability that z greater than 5.6. Okay? Okay. So again, the table gives us the area to the left, not to the right. So we will apply the complement rule, 1 minus probability that z less than 5.6. And don't forget, we have 2 before it. So it's 2 times this. From the table, you will look for the area to the left of 5.6. This one. And you will find it is equal to 1. Actually, when you go to the table, you will not find the 5.6. The maximum number is, I think, 3.99 or something like that. But any value for z greater than this value, the 4 point something, you will find the probability is 0.99999. So it's 1. So directly, any value for z greater than the largest value in the table is 0.999 or 1 directly. Okay? Now, you can find the b value. So you have here 1 minus 1 is 0 times 2, so it's 0. Okay? So the b value is equal to 0 in this case. Or you can use Excel function. All you need just to write this function in Excel. So it's 2 times 1 minus nor.s.distribution. The test statistic value and the true because it's a cumulative probability. So you will have at the end is equal to 0. Same thing. Okay? Okay, now we will compare between b value and the significance level 0.05. What do you think? B value is 0. The significance level is 0.05. So which one is greater? Of course, the significance level. So according to our table for the decisions, we reject H0. Why? Because the b value is less than 0.05. So we reject the null hypothesis. So what that means? That means the sample does provide strong evidence against H0. Okay? That means the dogs can know if the patient has cancer or not. Okay? Of course, this doesn't make sense, right? There is no something like that. Okay? Okay. So because of that, we have this insight. First of all, the sample here is not random sample, actually. It's a convenience sample. And if you remember, if we return to the type of sampling we have a random sample, stratified, systematic, and we have one of them, we call it the convenience sample. And we said that the convenience sample, we cannot use it for what? For inference. Why? Because it's a biased sample. Okay, so we cannot use it for making any inference about the parameters in this case. So this is the first thing. The second thing, of course, because it's a convenience sample, so it's not a random sample. So, of course, this comes from this. Because the sample is convenient, so it's not random sample. And of course, according to that, okay, any inferential from that, it will be just a tentative. Okay, it's not valid inferential in this case, or predictions in this case. Okay. Okay. So this is the summary for the alternative hypotheses. We have right-tailed test, left-tailed test, two-tailed test, I said to you. And when we report the p-value, it's more important to say that it's statistically significant at and the level of the significance level 0.05 level. Okay? So this will be more informative when we give the final conclusion. If you have significance level 5%, that means the confidence level 95%. Always the significance level is the opposite of the confidence level. So if you have significance level 5%, that means you have confidence level 95%. If you have significance level 10%, that means you have confidence level 90%. Of course, this is the opposite, okay? Same thing, if you have significance level 1%, that means you have confidence level 90%. Okay? And usually when we construct the confidence interval, we use what? 95%. So we use significance level 5%, as you can see. Okay? But so it's so important to say it's statistically significant at, and then the significance level we use for the test. Okay? Of course, the p-value has will inform us if the evidence is strong enough or not. Maybe you have two p-values, but one of them give us an indicator that the evidence with it is stronger than the other one. Like here, suppose you have p-value 0.001 and another p-value 0.049. Which one is statistically support the or have strong evidence than the other one? Of course, this one. The smaller the p-value, the stronger evidence against H naught. Okay, so 0.001 provide much more evidence than the other one with 0.049, as you can see. Okay, so it's more statistically significant than the second one, 0.00. Okay. Okay. So when you have a problem about the hypothesis testing, it's very important to decide if it's a one-tailed test or two-tailed test. As I said to you, this is very important, because if you have correct hypotheses, null and alternatives, and also the direction, everything after that is correct. Okay, because the p-value, you can calculate it based on the direction of the test. So it's very important to know if it's a left-tailed test, right-tailed test, or two-tailed test. And this will be obvious from the question. Okay, so for example, if you have words like greater than, exceeds, increases, at most, all these words means greater than. So the alternative would be greater than in this case. Okay, of course the opposite would be less than. If you have the two directions like greater than or less than, better and worse, change, just change, or different from, or deviate from, all these words means you have here the two directions. Okay, so in this case you have two-tailed test. You have two-tailed test. Okay, so it's very important to know the direction of the test from the very beginning, so everything after that will be correct. Okay, don't forget that the confidence intervals are two-sided test. In our examples, we said what? Do you remember when we give you the confidence interval, and I said to you, suppose someone comes to you with this value, so you will look at the confidence interval. If this value within this range, so his claim is true. If not, so it's not true. So the confidence intervals are two-sided tests. Don't forget that. Okay? So you can use the confidence interval as a two-sided test. Okay? In this case. Okay. So this is the end of hypothesis testing for the population proportion. Okay? So we still have just one more test. It's about the average. Okay? And this will be the last topic in our class for Math 2 24 this semester. Okay, guys?